Hi, Assalamualaikum. My name is Fatin NASUHA binti Shamas and my matrix number is 278062. Okay, today I want to present about assignment 1 that I study and research on 2 articles where I found on ACM Digital Library. So for the article 1, I searched for the topic which is preemptive trade block scheduling with online structural runtime prediction for concurrent GPGPU kernels. And for the second article, where I found temperature aware trade block scheduling in GPGPUs. So this title where I choose from the topic 3 for the trade states where the block state. Okay, so let's begin with the article 1 for the introduction, where the current trade block scheduling policy on video GPUs can result in significant loss of performance and fairness, and its proposed solutions were aim to improve performance and fairness by using estimates of kernel runtime to determine scheduling decision. Okay, so let's move on the proposed solution, where it is using the shortest remaining time first SRTF and SRTF adaptive, which is two new trade block scheduling policy purpose in the article. SRTF use estimates of kernel runtime to schedule three blocks with the shortest remaining execution time first, and for the RTF adaptive is an extension where the SRTF that adapts its scheduling decision based on change in workload characteristic. Okay, so for the online runtime predictor in this article, which it is proposed policies use a novel online runtime predictor for GPU grids to provide estimates of kernel runtime, and the predictor is based on an observation that the GPU kernel execution time is approximated by a simple linear function of the duration of its thread blocks. Okay, so for the evaluation, where all possible 28.2 program workloads from the ERC bench suite were run on GPGPU Sim Simulator and modified to support execution of the current concurrent kernels, and this result show that the proposed policy improve performance and fairness compared to the current FIFO policy, which is first in first out, and SRTF improved system, which is throughput by 1.18 and average normalized turnout time by 2.25 compared to FIFO. Okay, so for the conclusion on this article 1, where the proposed policy improve performance and fairness in concurrent GPGPU workloads by using estimates of kernel runtime to make a scheduling decision, and for further work could build on this research by exploring other ways to estimate kernel runtime or adapting scheduling decision based on other workload characteristics. So for the introduction on article 2, which the thermal management is a critical challenge in modern GPGPUs due to the high power density and thermal heterogeneity of these devices, and the thermal hotspots can cause performance degradation, reliability issues, and energy inefficiency in GPGPUs. And in this presentation, we will discuss a novel technique called temperature-aware trade block scheduling, which is called TAPS, that addresses these challenges. Second, this article proposed solution, TAPS is a thermal management technique that intermixes trade blocks from multiple thermally heterogeneous kernels to reduce thermal hotspots. TAPS also exploits the data parallel computation pattern of GPGPUs, the short lifetime of trade blocks, and the abundance of trade blocks to achieve its goal by itself. And unlike other thermal-aware workload scheduling techniques for CPUs that require trade migration, TAPS intelligently intermix kernels without doing any thread migration to eliminate that overhead of context switching. So for the proper solution, I talk about it. We have the intermixing algorithms in this article 2, which types offers three classes of intermixing algorithm. First, which is temporal alternate. Second, which is spatial mix, and last, spatial temporal, which is mixed alternate. And the temporal algorithm alternates between different kernels over time to spread heat evenly across all processing elements. And for this spatial algorithms mix trade blocks from different kernels within each streaming multiprocessor to avoid overloading any particular SM, which is streaming multiprocessor with hot kernels. And last but not least, the spatial temporal algorithm combines both temporal and spatial mixing to achieve better load balancing and temperature reduction. Okay, so by the result of the article 2 that I study and research, and the experimental results show that taps can reduce computation slowdown by 60% on average relative to state-of-the-art techniques while meeting thermal constraints. And among the four proposed intermixing policy, alternate works best since it does a good job spreading heat over time. And mixed non-uniform and mixed alternate work better than mixed uniform since mixed uniform runs hot on the same subset of SM, while the other two do some kind of alternation of hot and cool kernels. So for the conclusion on article 2, TAPS is a promising technique for thermal management in GPUs that can improve performance, reliability, and energy efficiency. By intelligently intermixing thread blocks from multiple kernels, TAPS can reduce thermal hotspots without incurring significant overheat. Okay, so further research could explore other intermixing algorithms or apply TAPS to other types of parallel computing architectures. And for further work, where we can having the one possible direction for future research is to investigate more advanced intermixing algorithm that can further improve load balancing and temperature reduction in GPUs. Another potential area of research is to explore the use of machine learning techniques to predict thermal hotspots and optimize steps accordingly. And that's all for my study and research on Article 1 and Article 2 for this assignment 1. Thank you so much.